Alright, my name is Caitlin Baker. I'll be talking about optimal transport. And so in optimal transport, they started talking about that problem dating back to the 1700s with Mong. And well, basically what optimal transport is, it tries to find the most efficient way to transport anything from one location to another. And so he first made a problem in 1781, and then later in the mid-1900s, Kantrovic added to it. And one definition from a really interesting lecture that I watched was that it's the natural geometry for probability measures. So as you move from one location to another, any object that you move, and it also has to deal with area, volume, all that, so it has geometry applied. And the initial applications that they were interested in was moving Earth and also transporting soldiers. So one basic application would be you have this Earth, this is the playing field, right? But then you have this little hole that you gotta fill, but then you have all this dirt right here, right? And so they didn't have like bulldozers to move all this Earth to right here. So we have to find the most efficient way to transport that. And so in Mong's equation right here, we have, oh my gracious, we have basic values. The cost is C right here, the cost of transporting from Pi to n sigma I. So basically up here is, it defines Pi and Ni. Yeah. X contains all the Pi, so all this right here, this is X, this is Y. And to define each of these, we have points here. So like, for example, this is Pi, and we gotta transport it to Ni, okay? And in Mong's equation, which I think is the simplest one, we minimize the cost that it would take to transport Pi to Ni. And the sigma there, that allows for any permutation between the two. So any P1 to N1, N2, N3, so on, as you move from P1 to Pn, and for any number n. And then Kantrovic later came on with this definition, also applying matrices to it, and doubly stochastic basically just means that each row or column in a matrix sums to 1. And then Kantrovic also combined their two equations to get this, and the supremum is the minimum of the upper bound, so it's still minimizing, but just in a different way. Let's see. Okay, this is my old PowerPoint, but it's all right. This is a portion of the proof here, and what this article tried to prove was equating m to k to d, which is those two equations earlier. And this first part, we are going to try to equate k, m, and d. So we start out assuming that k is less than or equal to m, and we start with this right here, these two inequalities. So if we have sigma pi minus, or yeah, phi pi minus v pi less than or equal to the cost of J. So what we're going to do here is basically do what it tells us to, right? We're going to multiply the inequalities by I and j, which is the matrix, right? So if we apply this, we get ij plus this whole thing, and then aij. I'm going to go ahead and write this out. And so after we have all this, we want to sum it up so that we can take the minimum. And you can see right here we have the second part of our equation already done. So this is done right here. And then for this part, we can split it up. You can split any summation up, and you can also split the AIJs up equivalently. So you can get AIJ summation of PI minus AIJ phi of NI. Right, and the AIJs, those are 1 is doubly stochastic, right? So you get the summation of PI minus summation of phi NI, and that should be what we have to get D less than or equal to K. And so now that we've proved that D is less than or equal to K for K is less than or equal to M, we equate them all since it's like that. And now this is, all right, okay, cool, that's it.